Today, we're going to do something a little different. We're going to dive into a university course, syllabus of all things. Why? Because hidden inside is the foundational magic that powers so much of our digital world.
I mean, really think about it for a second. How on earth can your headphones hear the drone of an airplane engine and, in an instant, create a perfect anti-sound to make it disappear? Or how does your phone pick your voice out from all the noise in a crowded room? It honestly feels like magic, right? But it's not. Well, the answer is a fascinating field called digital signal processing, or DSP for short. And this syllabus? It's our roadmap. We're going to walk through it step by step to see how engineers learn to play with sound, images, and data on the most fundamental level.
So here's our game plan. We'll start with the big picture, then dig into how we peek inside signals, control them, totally reshape them, and finally, how this all connects to the crazy world of AI. Let's get into it.
Okay, so the first thing any good course does is tell you what you'll actually be able to do when you're done. And this syllabus, I love this. It frames the goals not as boring academic points, but as a brand new set of superpowers. So yeah, this is not just about memorizing formulas. It's about getting your hands dirty. It's about learning to look at a signal and see the story hidden inside. Building super fast algorithms that can keep up with live video, and even designing the tools to teach a machine how to listen.
Right, so if you want to manipulate a signal, you first have to know what it's made of. And that brings us to the first major tool in the DSP toolkit. It's called the discrete Fourier transform, or DFT. Now, that sounds intense, I know, but the idea is actually beautiful. Imagine hearing an entire orchestra play. The DFT is the math that lets you isolate the sound of just the violins, just the cellos, just the trumpets. It breaks the whole thing down into its core ingredients. But here's the catch. Doing that math can be slow. And for things like noise cancellation, you need it to happen like right now. That's where the fast Fourier transform, the FFT, comes into play. It's a brilliant, hyper-efficient algorithm for doing the DFT, and it's what makes all this real-time signal magic possible. Okay, so now that we can see what's inside a signal, the next logical question is, how do we control it? This is where digital filters enter the picture. And this is the perfect analogy. In your headphones, a filter is the bouncer that tells the low-frequency rumble of the bus engine, nope, you're not on the list, but it lets the higher frequencies of the podcast you're listening to right on through. They are unbelievably precise tools for sculpting our digital world. But, and this is key, there's no single perfect filter. The syllabus dives into two main types, FIR and IIR. One is famous for being super stable, which is perfect for high-fidelity audio where you can't afford any distortion. The other is way more efficient, which is crucial for something like a small smart device. It's a classic engineering trade-off. You've always got to pick the right tool for the job. Now, we can go beyond just filtering. DSP lets us change the very fabric of a signal. It's called multi-rate signal processing, and it's all about messing with how fast we sample the data. Decimation sounds destructive, but it's just a fancy word for strategically throwing away data points to make a signal simpler. This is the heart of data compression. Anytime you switch a YouTube video from 1080p down to 480p to save on data, yep, you're watching decimation in action. And interpolation is the exact opposite. It's the art of intelligently adding new data points to increase the sampling rate. This is what your 4K TV is doing when it takes an old movie and makes it look amazing. It's literally creating information that wasn't there to begin with, filling in the gaps to make it look better. Okay, and this is where it all starts to feel like we're living in the future, because all these amazing tools we've talked about, they become exponentially more powerful when you combine them with modern AI. This is really the big question that's driving so much innovation today. Once you've cleaned up and analyzed a signal, can you actually train a computer to automatically understand what that signal means? The answer leads us to signal classification. The syllabus mentions using machine learning to teach a computer what a signal is. This is the tech that lets your phone identify a song in a noisy cafe or helps a doctor's equipment tell the difference between a healthy heartbeat and a dangerous one. It is a massive deal. And finally, the syllabus brings it all home, because learning all these concepts is great, but it's not the end goal. The real point is to use them to build something new, something real. The whole course culminates in a big project where students have to find a real-world problem and then try to solve it with DSP. It's the ultimate test, right? Taking all that theory and turning it into a working system. It's not just an assignment, it's an invitation to create.
And that really leaves us with a final thought. From decoding brainwaves to designing the perfect concert sound, the tools of DSP are literally everywhere, shaping our reality. So the only question left is, if you had these superpowers, what would you build?